Welcome back once again, and as per my promise, in this lecture I am going to talk about the application of the AC to a series LCR circuit, okay, which has been shown over here, where all elements are R, L and C, and the element EMF, source of EMF, they are all ideal, okay. So I can write from the KVL. For L I can write, of course, this is the V, and V is equal to L di dt for across this inductive element, and is equal to R into I, okay, using Ohm's law across the resistor, and Q upon C across the where in this situation the current is flowing as it has been shown. This plate is positive from inside and this is negative when there is a value of I other than 0. So now I can write that the current is defined, I is equal to dq dt, dq dt, and so di dt will be equal to d2 q upon dt2. So I write this equation as L d2 q upon dt2 plus R dq dt plus q upon C is equal to Vm sin of omega t. And this is also written as, just to give you an idea, q double dot, second order differential with time, q dot, the first order differential with time, and of course no differentiation. So this plus this is equal to Vm sin of omega t. This is second order differential equation which we will solve later on. So in the first instance we use the phasors. Okay. One thing which you must bear in mind, that whatever is the current through R is the current through L is the current through C is the current through this source of EMF, because it is a series circuit. So that is what I am writing, that I will be equal to IR will be equal to IL will be equal to IC. I can say this will be the same through IX and IZ, okay, when we talk about them, right? The current I will be equal to Im sin of omega t, where Im is equal to capital I root 2 sin of omega t. This we have done before, so you understand what it is. And similarly, Vm is equal to V root 2 sin of, V root 2, that's all. Now, with our definitions of the voltage phasors and the current phasors and the relations of the voltage and current phasors for the different elements, I am drawing a phasor diagram where I have shown the value of I to be larger in size. Of course, this is in amperes and this is in volts. So the length has been shown more. You can draw a smaller length if you like, no problem. So look here, VR is in phase with R. So the phase difference is equal to 0. So on the same line we have VR and R. VL leads the current I by pi by 2 radians. So this is along the y-axis I have shown. I am not taking a angle for VR and VI and then like this and then like this. Okay, I am not doing that. Very simple, understandable, okay, along the x-axis and along the y-axis. If you want, you can just tilt the whole thing if you like so. VC leads I by minus pi by 2. That means this is the VC and this is the VL. And I have shown here that my VL is greater than VC. Okay. So first of all, this is the imaginary axis and this is the real axis. So I just add these two voltages, they are opposite to each other, and this much VC is from here to here, and so I get the resultant of the two. The addition of VC and VL comes out to be equal to Vx. Okay, where X is the reactance. So this is VR and this is Vx. They are perpendicular to each other and they add according to the vector law of addition. And I find that the net resultant voltage is given as V, which is shown over here, and we see that this resultant voltage leads the current by an angle phi, if this be the case, which I have just blown up to show you more clearly that this is our VR and this is Vx and this is our V. Okay, this one is our V. So you understand what's the relationship. This is the phi, this is my I. But if VC is larger than VL, then this will be more and this will be less. And so the resultant will be on the minus y-axis, and that is what I have shown over here. Just I, VR and Vx, where of course Vx is given by Vc minus Vl and XL is less than Xc. So this is the situation that exists. Okay. So Vx is equal to Vl minus Vc. We define it like that. It leads I by plus or minus phi. Okay. Sometimes this is more than 0, then it leads by some angle phi, and if it is less than 0, then it leads by some other angle minus phi. Okay. I'm using the word leads. You can also use the word lags behind if you like that. Okay. Now, V is equal to VR plus Vx is equal to Vz, and I have put the sign which shows that they are phasors. Okay. I have not put signs over there just to make it easy. If you want, you can put these signs here that it is okay. Now, if I have a right angle triangle like this is VR, this is Vx and this is V, then you can see that by our famous hypotenuse square is equal to base square plus perpendicular square. Okay, that theorem from the Greek days, then we find that V square is equal to VR square plus Vx square, and this V also write this V as we write as Vz, where Z is the okay. Z goes for the total impedance here or here. Okay. Anyway, now there is another relation that we should bear in mind, that VR will be equal to R into I, VL will be equal to XL into I, VC will be equal to XC into I, V will be equal to VZ will be equal to ZI. Okay, and Vx will be equal to X into I. So all these quantities R, XL, XC, Z, they all have V divided by I, and V divided by I is a famous friend Ohm's law, and said that, well, the unit will always be in ohms. Okay. Now, if I have this Vz and this as Vz square is equal to V square, then we ought to also define what is the value of phi. So tan of phi will become equal to Vx upon Vr, Okay, in either case or this case, and therefore phi is equal to tan inverse of Vx upon Vr. Okay, so this is the quick analysis of the circuit with the help of the phasor analysis. Okay, so from the various phasor diagrams, set of phasor diagrams that I have drawn here, okay, I can write the phasor V is equal to phasor R plus phasor L plus phasor Vc, which is phasor R plus phasor Vr plus Vx is equal to phasor Vz. Okay, and if I write this Ri, Xli, Xci, then Ri plus Xi is equal to Zi, where X is equal to the difference of XL to Xc. Okay, so Z square becomes equal to R square plus X square. Okay. But if we draw a diagram like this, then we have to understand that if I have a diagram of R, X and Z, R like this for example, X like this, and Z here, okay, Z like this, showing that Z is leading the current I by phi, R is lagging behind the current by another value of phi, as the case may be. Okay, but these, if this kind of representation is done, okay, then we have to understand and we have to bear in mind that these are not rotating phasors. They will stay there, just help us. Okay, so phasors in themselves, they help us. And now I just translate it into a series RL circuit where this capacitor will not be there. Okay, so RL, and then we have a similar kind of thing. Okay, V will be equal to VR plus VL, etc., and we'll have a VZ here, and this is what has been presented over here, right? So if in a circuit XL is greater than XC, if XL is greater than XC, or the voltage VL is greater than VC, even in this circuit, then we call this RLC circuit as inductive in nature. Else, if this VL is less than VC or XL is less than XC, then such an RLC circuit is called a capacitive. The circuit is supposed to be capacitive in nature. One thing which I'll leave for you is to draw the time diagram. So for the current you start like this, and then you have to decide an angle phi, and then you have to draw the voltage, and the voltage, because it leads this, and therefore it has to be something like this. Okay, like this, and you can check who leads, who lags, this, that kind of a thing. So that way we sort of finish off with the phasor representation of the series RLC circuits. Now we will go for this kind of a representation and do it with the help of solution of the second order differential equation. So stay with me. So let's try an analytical solution second order differential equation that we have over here, and let's try like we have done in the case of simple harmonic oscillations. Q is equal to Qm sine of omega t plus theta, where theta is any angle. So dq over dt is equal to I, and when I differentiate I get it as omega qm sine of omega t plus theta plus pi by 2, which turns out to be equal to cos of omega t plus theta, and this omega turns out over here. And similarly, if I differentiate it again with respect to time, then I get minus omega square qm sine of omega t plus theta. Okay. So putting these things in this equation, I find it minus L omega square, okay, L and d2q upon dt2 minus L omega square qm sine of omega t plus theta plus R omega qm cos of omega t plus theta plus qm sine of omega t plus theta. Okay. Now what is there? There is one angle, one function which is a cosine function, other functions are the sine function. We separate them together. So I can write it here, qm into omega r cos of omega t plus theta plus xc minus xl. Xc is equal to 1 upon omega c and xl is equal to omega l. Okay. So from here, these two I equate together and we get omega qm sine of omega t plus theta, and this we equate to Vm sine of omega t. Now the trick is that multiply and divide this whole expression on the left hand side by z is equal to, okay, z is equal to r square plus xl minus xc minus xl whole square. Okay. So what I get is that if I take q omega z multiplying and dividing, so z is here, r upon z into cos of omega t plus theta, and xc minus xl upon z sine of omega t plus theta. Okay. Now this part I take it as cos of phi, some another angle, and this part here I take it as sine of phi. So it is basically a value which we can get from a right angle triangle. Okay. So tan of phi, this divided by this turns out to be equal to xc minus xl upon z divided by r by z, and z they cancel out, so xc minus xl upon r. Okay. So that my my new angle phi becomes equal to tan inverse of xc minus xl upon r. Okay. So going further, so we got this relation over here where phi was tan inverse of xc minus xl upon r. Okay, and we obtained the results. So let me write this again with qm omega z cos of phi cos of omega t plus theta, sine of phi sine of omega t plus theta, where the values of cos of phi and sine of phi are expressed over here. This is one of the techniques of solving trigonometrical problems, equations like that, and this is equal to qm omega z cos of omega t plus theta minus phi, okay, which we equate to our Vm sine of omega t, the applied voltage. This is so because cos of A minus plus B is given as cos of A cos of B plus minus sine of A sine of B. Also, we have to bear in mind that the cosine is a symmetric function, and therefore cosine of any angle minus A is equal to cosine of angle A. Okay, so when we put and compare this side to that side, okay, so Vm turns out to be equal to qm omega z, and this sine of omega t must be equal to cos of omega t plus phi minus phi. And if so, then what we obtain is that theta minus phi is equal to minus pi by 2, or theta becomes equal to minus pi by 2 plus phi. Okay, so this we can substitute, and what I obtain is that Im is equal to Vm upon Z. This is equal to Q m into omega, or omega into Q1, so that the equation becomes equal to I is equal to Im cos of omega t plus phi. Okay, as I is defined as dq upon dt, so Q is equal to Qm sin of omega t plus theta. So we get this relation as Qm into omega into cos of omega t plus theta, which I can write as, because theta is equal to minus pi by 2 plus phi, so this becomes equal to cos of omega t minus pi by 2 plus phi, and this comes back to the format of sine. So I get this Im, which is Qm into omega sine of omega t plus phi. Okay, so this is the relation that we obtain. Okay, and here of course, like I said there, Im is equal to Q into omega. Omega has the dimensions of 1 upon time, 2 pi upon capital T. Okay, so charge divided by time, that gives us the current. So if I go back to this, then I can write this Im as equal to Vm upon under root of Z. I can write as, this has been defined. Okay, Z is equal to under root of r square plus xc minus xl, or difference xl whole square. Okay, and tan of phi is equal to xc minus xl upon r, as has been obtained over here. Okay, so this is the way. It's a very long way, and this is how we solve the problem of RLC circuits. The same kind of mathematical analysis and alternate analysis can also be carried out for RC circuits and also for RL circuits, but I'm not going into that. It's always good that we go for the phasor method. The phasor method is a very readily made thing. I just told you that if you had any doubts that why you are not taking the equations and why you are not solving them, then this is the way that the equations are solved. But it's lengthy. You can do it once or twice, but always for the sake of solving your questions, just draw the VI curves, that is the phasors, determine the value of the lead or lag, whatever is there, and that is, you can obtain the things in the manner that I told you before. So thank you very much. Next item that I am going to take is RLC circuits and their resonance properties. So wait for that. Let's meet again. Thank you very much.